So for part A of this problem, it's pretty straightforward. What is the energy stored in the spring? So that's the spring potential, US. And we know the equation is 1/2 kx squared. We know the spring constant K, 400 newtons per meter. And we got to be careful, as always, the problem is given in centimeters. 40 centimeters is a stretch, so we have to make sure we convert that to meters, 0.4, and we get 32 joules. Now for part B, since we're trying to find how fast the mass is moving right when it leaves the spring, again, we're converting this potential energy in the spring into kinetic energy. So that energy is going to get transferred. Now one thing to keep in mind here is that some of it is going to get lost to heat because this surface is not frictionless. It's got a coefficient of friction of 0.23. So we start off with 32 joules initially, when the mass is at rest. Then the mass is released, the mass and spring system start to move, and as it leaves, it's going to have some velocity, which is what we're solving for. We know the mass of the block, 2 kilograms, solve for v from that v squared, but again we have to also include the fact that some of that is being lost to heat. Now heat is a form of energy, and whenever we lose heat due to friction, there is work being done by friction. So we know that work is equal to force times distance, specifically the force of friction in this case, because that's what's providing the heat. So we know force of friction is the mu, coefficient of friction, times the normal force. Now this is a flat surface. It's not a ramp or anything like that, so the normal force is simply the force of gravity, so mass times gravity. So that whole component there is your force of friction times the distance that it slides. We want to know how fast it's moving right when it leaves the spring. Well, it's going to leave the spring right when that spring reaches equilibrium, which is 0.4 meters from where it started. So we plug that in for our value for D, and we do a little bit of algebra, solve for V, and we see that it's 5.5 meters per second. Part C, pretty straightforward. What is the frictional force? In this case, frictional force is constant throughout. It's just the force depends on the coefficient of friction and normal. And we actually already kind of technically solved for it in Part B, but we're just kind of isolating it now. So the force of friction comes out to be 4.5 newtons. Now for Part D, how fast is the mass moving at the edge of the table right before falling off? Very similar to Part B. And there's actually a couple ways you can do this. The way I did it is from the very beginning, right when the mass was released, to the point when it basically leaves the table. Now you could look at different points in time. You could use the initial point being when the mass left the spring, and obviously then your numbers will be a little bit different. But the way I did it, so I set it up, initially it's only spring potential at the very beginning, 32 joules, and that gets converted to kinetic, which we're solving for that velocity again, just like Part B, plus same thing as before. We know that some of that energy is going to be lost to heat. Now we already know the force of friction, 4.5 newtons, times the distance. Now you'll note that the distance 2.4 meters. Where did I get that? If we look up at the initial diagram here, we see that the 2 meters is really from where the mass leaves the spring. Well, again, I started this problem when the mass was when the spring was compressed with the mass attached to it. So I have to add that little bit, that 40 centimeters, 0.4 meters, to the total distance that it slides to the point where it reaches the edge of the table. So that's how I set that up, and I do, again, a little bit of math, and the velocity is 4.6 meters per second. And again, this makes sense. You look at Part B, clearly it's going to be a little bit slower than the answer to Part B, because as we know, as a mass slides across a surface, it constantly loses heat because of that friction. Now finally for Part E, this problem is really a projectile motion problem. So how far from the edge of the table does the mass hit the ground? Before we can figure out how far, we need to know how long it's in the air, and that depends on the vertical component of its motion. So we know that the initial velocity, and this is where we got to be careful, initial velocity in the vertical or y direction is 0. It technically starts from rest, vertically speaking. So we know that it falls 1.5 meters, and V naught goes away, V naught T, and we have 1/2 a acceleration of gravity, t squared, solve for t, and we see that it's 0.55 seconds. And then to figure out how far from the edge, we know that horizontally speaking, when we talk about motion, projectile motion, horizontally motion is constant, speed is constant, so distance equals speed times time. That speed that we're using is the speed right when it leaves the table, which we got from part D. So 4.6 meters per second times how long it's in the air, and we see that it lands 2.55 meters away.